Hey guys, so let's start our exploration of maths with a very basic and a very fundamental concept called the set. For the purposes of illustration in this video and probably all the videos that I make after this, a set would be represented by an ellipse or a circle with a name like S, or I think this is omega, maybe lamp. I don't know what this is, but this ohm symbol or whatever it is, or this, or my personal favorite, names like animals. I mean nouns like animals, or something like rivers. So all of these are sets represented by ellipses and their names. So this is just a representation, and that is how we are going to visualize sets. Now, this is probably a good point to tell you that I'm not a mathematician, and all of the things that I say in this video are going to be sort of accurate. I'm not claiming that I have any sort of professional mathematical knowledge, and I definitely don't have the rigor that you would get from a PhD in mathematics or anything like that. What I do have is a deep appreciation of mathematics, and I see its utility in daily life, and I think it is really cool, and I want to show you why I think it is cool. So with that, let's start with the concept of a set. So a first question, and a very natural question that arises, is what is a set? And you might have or might not have heard this definition before, but it says that a set is a collection of distinct objects. Now, I don't really like this definition as a definition because it has these words: collection, distinct, and objects. And the reason is the word collection itself is a lot like set. In fact, I have seen a definition of collection which uses the word set, so you get a circular definition if you are to take this, if you were to take that definition of collection. So I don't want to use that. What I would rather do is treat set as an axiom, which means that we thoroughly understand what a set is intuitively, and then we treat it as the base or the foundation upon which we will lay our groundwork and everything beyond that. An axiom is something that is assumed to be true, and we are going to treat our set, or the concept of a set as an axiom. So now, instead of looking at this as a definition, we are going to look at it and treat it as intuition. And I love that, because now we kind of get a feel for what a set is. It is essentially a container in which we can put different objects. And that is exactly what a set is, honestly. In terms of concept, in terms of an idea, that is what a set is. Very briefly, let's talk about this word, an object. What is an object? An object is anything that you can treat as a distinct unit. And again, this is not a definition of the word object, but more of an intuition as to what an object is. For example, if you have a group of people and let's say they belong to the same family, and if we are going to research a set of families. So this is the set F of families. Then F1 can be a member of the set or can be an element of the set. And for that purpose, we can treat F1 as an indivisible unit, and we don't have to treat its members separately. So for the purposes of set F, which only deals with families, where F is a set of families, F1 is its element and F1 is an object. So I hope that is clear. But this gives us an opportunity of delving into something or some of the lingo and some of the jargon associated with sets. So I'm just going to quickly write down all the jargon that we are going to deal with. This is something, all of these are symbols by the way. This is something called, this is read as belongs to. This is called subset of. This is a proper subset symbol. This is the union, this is the intersection symbol. And this is the union symbol. So I think we can start with the most basic and I think the most important belongs to symbol. Well, when I say most important, I mean in terms of understanding everything else. Once we understand what belongs to does or what belongs to means or what it signifies, then we can very easily understand all of these other symbols, and I'll show you how in a minute. But before we begin that, we need to understand a very central concept, which is that of a property. What is a property? A property is basically a constraint. It tells you something about the object or the group of objects. For example, if we look at a set 246, very easily we can see that all of these are even numbers. So the common property that they have is that they are all even. So we can call it property P1, an element is even. So I think you are supposed to understand this intuitively. I don't think I can define what a property is for you, but I can tell you that objects have properties, and as far as sets are concerned, and more specifically set building is concerned, properties are the central and the most important things in order to construct meaningful sets. So what do I mean by that? Let's say that we have a set. A very good question to ask would be, how do we construct a set? I mean, we can construct random sets. We can just say a set of ideas, let's say, a set of other sets, a set of numbers, stuff like that. And all of these are excellent examples of sets, and they show you the breadth of maths because we can actually have a set of ideas and that is a valid set, or we can have a set of other sets and that's also a valid set. But is that a particularly useful set? Not really. But as math is about utility and making stuff that works, let's constrain ourselves to meaningful sets. Meaningful and useful sets. And that's exactly where properties really shine. When you have to build meaningful and useful sets, you need to use properties. An excellent example for this would be the set of prime numbers. So let's actually try to build the set of prime numbers. How would we define that? And that's where the properties come into play. We define prime numbers using this logic. So we have an element, and if x is prime, x has to be a natural number. So we say that x belongs to the natural number set. And then we have another property, right? So if we have x mod y, which basically means that after division by y, the remainder is equal to x. That is one of the most fundamental properties. We also have y belongs to natural numbers, and we also have y not equal to x. So we can just tidy it up and kind of write it nicely and cleanly in set builder notation. So this is the set builder notation, and we can define the set P of all prime numbers as the set of all x. So the curly bracket basically means set. So it's saying it's a set of all elements such that x comma y belongs to natural numbers, y is not equal to x or x is not equal to y, doesn't matter, and x mod y equals x. So this is set builder notation. So what we essentially have is element, and what we have here actually, this is like a conditional. This is not exactly a property, but that's fine. So what we have here is the element, a property, a condition if satisfied, and then another property. And that is how you define sets. So a set is defined using properties. And now I want you to think about sets definitionally as definitionally equivalent to elements or objects satisfying properties. So if I say something like x satisfies property P, and the set S is a set of all elements, let's say E, such that E satisfy such that E satisfies properties P. And remember, this can be a set itself, so it can be a group of properties. So let's say that an element X satisfies property P, and then if you have S, which is defined as the set such that every single element satisfies properties also in P, then it must mean that X belongs to S. So these two are the same things. And henceforth and always, we are going to think of sets as elements which satisfy properties. I think this is going to be really useful when you start programming and when you start programming math, because in mathematical programming, when you think of a set and when you're constructing sets, this property comes in really handy, or this definitional equivalence comes in really handy. So we have defined what belongingness means. It basically means that an element satisfies a property. So instead of belongs to, you can also literally write it satisfies a property. Now that we are done with this, let's go and look at another concept called a subset, and it is demarcated using this diagram. So you have a bunch of elements in a set S, and you have a smaller set within S, and it is demarcated by the set Q. So what can this mean? It is in the basic, or in the most, it's in the purest form, specification. Let's say you have a set of properties P, and you have another set of properties. So let's call these P1, and you have another set of properties P2. And when you construct the set, you have actually used all the properties from P1 to construct the set S. But while constructing the set Q, you are using both of these. Do you see what is happening? You have a set Q or a subset Q of S, which not only satisfies properties P1, but it also satisfies properties P2. And that is exactly what a subset is. Now, here is the most amazing part of a normal subset. It is not necessary that the cardinality of Q is less than the cardinality of S. Cardinality is basically the number of elements in a set. So what do we mean by this? Let's say we have a few properties that we could identify in the initial set S. And later, upon closer inspection, we also found that every single element of S also satisfies another bunch of properties P2. So now we have a set P3, which is P1 plus P2, and we find out that the newly created subset Q has actually all the members of S, because all the members of S satisfy both of the properties. So it is not necessary that a normal subset has a smaller cardinality than its superset. But if we have a pure subset relationship, then that is absolutely true, because it means that there is at least one element belonging to S that satisfies only properties P1 but does not satisfy properties P2. At least one element. You need at least one element in S that does not satisfy P2 to have Q as the proper subset, to have Q as the proper subset of S. So that's what we mean by set, subset and proper subset. So we have done this, we have done this, and we have done this, and now we are going to go to the final part, which is unions and intersections. And once again, thinking about it from the perspective of properties is super helpful. Let's say you have two sets. I'm drawing them without an intersection for a reason. So let's say we have two sets. Let's call them S1 and S2. And for some time, let's just chain them to P1 and P2. P1 is a set of properties that S1 satisfies, and P2 is the set of properties that S2 satisfies. Now, if we have a group of elements in S1 that also satisfy P2, then what we have is a union. Because if we have elements which satisfy P2, so let's say that we have let's call it Q. Q1 is a subset, a proper subset at that of S1, and then Q1 satisfies P2, then by definition Q1 belongs to S2. And that is this part, and this is what we call an intersection. So it is all about properties. If we can find a group of elements from S1 that satisfies these properties, then we can say without a shadow of doubt that there is an overlap between these elements. The group of properties or the set of properties that this intersection satisfies is P1 plus P2. And the keyword for S1 intersection S2 is and that's how we get the relationship between and addition. It's through this relationship of properties, which I think is super neat. So that is what an intersection is. Let us try to figure out what a union is. A union is even more straightforward. So if you have two sets, and again now I'm drawing them disjoint, and again it is the same exact setup. Now a union is something which is basically take any element either from here and here, and what we are dealing with essentially is if X, an element, satisfies either P1 or X satisfies P2, and as you can see now I'm even writing it in that way. I can say an element satisfies a property, but it actually means the same as X belongs to S1, or we can say that X satisfies a property P2, but it would be the exact same thing as saying X belongs to S2. So if X belongs to S1 or X belongs to S2, we have X belongs to S1 union S2. And the keyword here is OR. So that is how we deal with belongs to, subset of, proper subset, intersection and union in the context of a set and in set theory using the keyword properties. And I think this is a good point to end the video, but there is one thing that I want to discuss which I don't fully understand, which I actually would love to hear from you in the comment section if you know why, and that is the empty set phi. So that is the set with no elements. So, or it's called a null set. And if you had asked me, I would say that the empty set satisfies none of the properties. But the way the empty set has been defined is that it satisfies all the properties. So an empty set is a subset of all sets. And it is unique. The uniqueness I kind of understand intuitively, but this whole notion of an empty set satisfying all the properties is something that I can't fully wrap my mind around, but I think it is super cool. So yeah, I think this is the point. And also, by the way, empty set is these are like all things that are used to denote the empty set. Null, phi. I think sometimes you only have phi, but usually it's a phi within the curly brackets, or it's just curly brackets. And it's a subset of all set. It's a subset of any set and all sets, and it is unique. So yeah, thanks a lot for watching this video. Please give me feedback, as I would love to improve this, and tell me what I could do differently. Thank you.